In this tutorial video, I will introduce SAKI, a computer program for simulation and analysis of Kikuchi pattern. This is one of the components in Landyne software suite for electron diffraction simulation and crystallography analysis. You may download the software suite from the websites on the screen. Here is the Landyne Launcher icon. Double-click the icon to activate the launcher. If you have a license file, please copy the license key to C/Landyne3/programs/. Let's check the software and license key in my computer. This is SAKI 3 and the license key. Click this button in the launcher to start SAKI 3. A license dialog will pop out if you don't have the license file. In this case, you may select the demo mode to continue. Let me briefly introduce the functions of SAKI 3 first and then go to the details of each function with examples later. The main frame with a display area, together with the simulation control dialog, will appear after the software is on. In Crystal menu, the functions are: to create a new crystal file using a template, to load crystal file for simulation, to exit the software. In Experiment menu, the functions are: to load or erase experimental diffraction pattern on display area, to process experimental diffraction pattern, including contrast inverse, pattern resize and rotation and position adjustment, to add reciprocal spacing marker information, to analyze experimental pattern for index, and to determine the precise orientation. In Simulation menu, the functions are: to select to microscope high tension, thus the wavelength, to change the reciprocal range of Kikuchi lines, thus control the calculation time, to manage how index labels appear on display area, to convert Miller and Miller-Bravais indices for hexagonal system, to erase the simulation pattern. In Pattern menu, the functions are: to define the region of interest for print and dot per inch for output in TIFF format, to save the output in JPG and TIFF formats. In Table menu, the functions are: to provide an interactive periodic table of elements and a table of space group numbers and symbols. In Option menu, the functions are: to select the look and feel of the software appearance, to hide or show the graphical menu bar. In the Help menu, the functions are: to retrieve the information about the hard drive label and serial number on which the Landyne software installed, to retrieve and check the version of the software. The serial number will be used to generate the license file. Please take a snapshot of the serial number dialog and send it to Landyne when you purchase the licenses. Please check the update software information on Landyne website regularly, so you will always use the most recent version of the software. Landyne software suite is distributed with a collection of structure files, so you can use SAKI 3 immediately. You can create a new structure data with a template in SAKI 3. The usage of the template is self-explained. You may also follow other Landyne tutorial videos, for examples, SVT, SAED 3 and SBIC 3, on the details on the usage of the template. The format of the structure is simple, and you can open it in text editor. However, you may have trouble if you write the format not exactly as required. We recommend to use the template to create a new structure file. We suggest to view the structure with SVAT2 after you create a new structure file. SVAT2 is this one. It will help you to check if the structure has problems or not. SVAT2 also provide a function for you to convert structure file in other format, for example, CIF, to the format we use in Landyne software suite. Now let's do the simulation. The default value of HT is 200 kV. Reciprocal range for the generation of Kikuchi lines is medium range. You may change these values in the simulation menu. Structure file for the simulation can be created and then loaded in Crystal menu. Let's use the default file, the FCC aluminum, to simulate the SAED pattern with Kikuchi lines. Click Simulate button. This is the diffraction pattern along the zone axis of 001. Change the zone axis to 1, 1, 1, and then click Simulate button. Change the zone axis to 0, 1, 1, and then click Simulate button. Change the reciprocal range if necessary. Large, medium or small. Now let's change the tilt angle of X, Y, and set X equals 0.5 degree. Click Simulate button. Now bring the tilt angle back. The appearance of the simulated diffraction pattern can be changed in pattern size, overall intensity scale and orientation. Change the pattern zoom. Change the intensity scale. Change the orientation angle. The horizontal mirror plane allows to index the same pattern in the second way. The spot pattern can be displayed as in circles or discs in various colors. We can render diffraction, spot pattern, and Kikuchi lines separately. The labels of indices can be chosen according to the diffraction intensities for both the spot pattern and the Kikuchi lines. The positions of the index labels can be adjusted. Double diffraction effect can be included. The spots and extinction positions will show up due to the double diffraction effects. Lowy center and base vector can also be added on in patterns. Now let's use a demo to illustrate the analysis of the experiment pattern. The experimental diffraction pattern can be loaded by using the drag and drop box. This experimental pattern was taken from a chromium-3 germanium phase. The pattern can be resized and rotated to a suitable appearance. The incident beam position is adjusted to the center of the display area. The number of circles and n-fold symmetry can be set up in the adjustment dialog. Now let's invert the contrast. Load the structure file of the CR3GE phase and do the simulation. From the spot pattern, we can determine the zone axis is 2, 1, 0. In the simulation, we have the indices for the Kikuchi pattern. The spots and extinction condition appear on the experiment diffraction pattern due to dynamical diffraction effects. We may turn on and off the double diffraction effects to show the simulated pattern. This analysis dialog is designed to find the zone axis and the precise orientation of the surface normal along the incident electron beam in electron microscope. An example, Kikuchi pattern of magnesium, is taken from Eddington's book, Practical Electron Microscopy and Materials Science, Monography 2, Electron Diffraction in the Electron Microscope. We already show how the drag and drop method in the example above. We load the diffraction pattern using the file system this time. The calibration of pattern zoom was measured to be 1.18. Usually this value can be measured from the scale bar in experimental electron diffraction pattern. In the current case, we don't have the scale bar, so we derive the value from a pair of Kikuchi lines and its index in the book. Click Analysis and Experiment menu to activate the analysis dialog. We need to mark 3 pairs of Kikuchi lines. For each pair of Kikuchi lines, we need to define the width and angle in the corresponding fields and use the mouse to point to the position. And then search the HKL values for the pairs of Kikuchi lines. A list of HKL values is generated using the tolerance values of G and angle, and saved to a text file. In the current case, we have the indices as 0, 1, 1, 2, minus 2, minus 1, minus 3, 2, 1. Those indices are used to derive the zone axes of 3 Kikuchi poles. And then we should check their relation in SAED, the software for stereogram application in Landyne Suite. When the positions of 3 zone axes are matching well to the positions of the 3 Kikuchi poles, it means that the zone axes are correct. Use the mouse pointer and wheel to mark down the position of incident beam, and then calculate the precise orientation, which can be expressed in 2 formats: the angles to the Kikuchi poles and the zone axis expressed in fraction. For a hexagonal system, besides the Miller indices shown above, Miller-Brevet indices can also be obtained using this dialog in Experiment menu. The simulated images and the analyzed processes can be saved to image files. Firstly, we should set the size of the region of interest, briefly as ROI, and the value of the point per inch, briefly as PPI, for TIFF file. Click the ROI and TIFF in Pattern menu to activate the dialog. Check the show box and adjust the ROI size. A blue square indicates the area to be saved as image files. PPI is usually set up as 300 or higher. Image file can be saved in TIFF or JPG formats. The PPI works only for the TIFF format. A tool for the conversion between Miller and Miller-Brevet index for hexagonal system is provided. Click the Miller and Miller-Brevet indices in the simulation menu to activate the dialog. Select either reflection index or zone axis index to do a conversion. Both ways work from Miller to Miller-Brevet indices or from Miller-Brevet to Miller indices. For your information, the closely related software to SAKI 3R, SVT2 for display of crystal structures, SAED 3 for simulation of diffraction spot pattern. SBIC 3 for stereogram-related analysis. User manuals are available for all the software. Please check the user manuals for more information. Thank you for watching. Please check our other videos on the Landyne software suite for electron diffraction simulation and crystallographic analysis.